everyone. This video, we are gonna finish the rest part of Chapter 1. Section 1.8, Logarithmic Functions and Model. A logarithmic function has the form a plus b multiplied by the natural log of x, where a and b are constant numbers, but pay attention to the pay attention to the b. It cannot be 0 because when b is 0, this is a constant function. And the input, because it's natural log of x, the input value x must be positive. X cannot be negative. And then this function, a logarithmic function, is actually the inverse function to an exponential function. So in last section, the end of last section, we talk about the inverse function. F of g of x is x, and g of f of x is x. And in the function graph, we can use the horizontal line test to test if a function is a one-to-one function. For a function, if it is a one-to-one, then the function has an inverse function. And the inverse function of an exponential function is a logarithmic function. So we talk about for the exponential function has only one concavity, and similarly the logarithmic function also has only one concavity, and the concavity is determined by the sign of b. If b is positive, then the function is concave up. If b is negative, then it is concave down. So for this one, it has a vertical asymptote at x equals to 0. And for an exponential function, it has an horizontal asymptote. So when b is positive, the end behavior of the function is like positive infinity. When b is negative, the end behavior of the function is negative infinity. So for this one, we talk about both of them. We talk about positive infinity. We don't consider when x goes to negative infinity because x stops at point 0. So you can see if this is a function graph. So actually, when x goes to 0, then the limiting value actually the function goes to negative infinity. So we don't consider when x goes to negative infinity for a logarithmic function. But you can see exponential function and a logarithmic function, they are inverse function. And for the inverse function, they are symmetric over the y equals to x. So this is the first case when the exponential function is the constant number, the coefficient is positive. So this is the corresponding logarithmic function. So you can see, all right, they are the same. They look like this one. And then this is the second case of the exponential function. So this is a decreasing function. Exponential function is either this one or this one. Or this one. So this is just as the first case, and this is the second case, which is right here. So let's see the second case. Second case, because this is the inverse function of an logarithmic function, so they are symmetric over the y equals to x. So you can see, all right, now they are symmetric. So this is the second case of the exponential function and the corresponding logarithmic function. So only one concavity, a logarithmic function has one concavity. And this one has a horizontal asymptote. And for a logarithmic function, it has a vertical asymptote. And similar, for the exponential function, the horizontal asymptote is right here. And for the logarithmic function, the vertical asymptote is right here. And they are symmetric over y equals to x. And let me see. All right. So, again, for this one, you can see for the two logarithmic function, both of them x must be positive. So for a logarithmic function, we don't consider the case when x is negative. That is right here. The input value x must be positive. And example 4. Alright, so here it shows you how to get the equation for logarithmic function. So here, linear function is 4, quadratic function is 5, cubic function is 6, logarithmic function is ln is 9. So everything else is the same, and then we use zoom 9, zoom fit to see if our model is the correct model. And example 4. So example 4, we are given a table. The first one asks you, okay, you can pause the video and try to redo it by yourself. Example 4, A, B, C, D. Alright, what features? So first, for this one, because we are only given the data table, we are not given the scatter plot. So first, you have to draw the scatter plot by yourself. And from the scatter plot, then make your decision which kind of model we're going to use. So for this one, because it has only one concavity, and it is concave up. Excuse me, it's concave down. With an increasingly slow increase in the concentration of the drug. And then we use the logarithmic function, and B already completely defined the logarithmic function. So the full model should be the equation gives the output description blah 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 blah. It has four parts, but for this one I just gave you the equation. The rest part is too long, so I think most of you have the solution. Natural log of x. So this is the equation, and don't forget the unit. The unit is output unit per input unit. Output unit is this is the output unit. Input unit is excuse me. This is not the derivative, so we just use the output unit, that is mu g per ml. And this one gives the output description blah 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 blah. So just finish the rest part. And then example C, the answer is just A. 7.821 mu g per ml. And example D is according to the pay attention to the unrounded model. And rounded model, so that means you cannot. Alright, so you can see here for this one. This is our unrounded model, so you can see we have a lot of decimal places here. So you can just use this model, not the rounded model. Rounded model just means you use 3 decimal places instead of all of them. So use this model, not just the rounded model. And then if you get a different answer, that means probably you use the rounded model or something wrong with your equation. And then example D just asks you try to solve for the equation. P of x is 8.5, and what is the y of x? So you use math solver, and the x is 27.166. This is section 1.8. Next, let's review section 1.9. 1.9 is a quadratic function. So for a quadratic function, is ax squared plus bx plus c, where a cannot be 0. Because if a is 0, then this function is a linear function, not a quadratic function anymore. And for this one, it has only one concavity determined by the sum of a. So if a is positive, then the function is concave up. If the a is negative, then the function is concave down. And if the function is concave down, so for example, concave down, excuse me, this is concave up. For example, if the function is concave down, then we can see we have a maximum value, and the end behavior must x goes to infinity, x goes to negative infinity. Both of them goes to actually negative infinity. And concave up is similar. So this one is straightforward. And let me see. So for this one, this is the function concave down. This is concave up. And alright, for the instruction part, for a quadratic function, we just use 5. Then the rest of the part is the same, and so you can see here. It shows alright, our model is a good model. And so page 61, right here. The second difference, we know for a linear function, the first difference is all approximate a constant number, and for the quadratic function, you can just check the second difference. And then as example 4, this is example 4, and example 5. Alright, for example 4, still the first step is to plot the scatter plot for the data. Then you can see, because positive and concave up, then we know we have to use the quadratic function, quadratic model. Then it is just 0 to 9x squared minus 2.28, excuse me, 286 plus 286x plus 79.685. %. So this one gives the help description, gives the exponents, where x is from 1 to 43. And the next one, so 45, then the answer is 36.407%. Alright, for example 5, an example asks you which type of functions might be appropriate to model this data. So for the first one, you can see the pattern is quadratic is possible, or exponential, because quadratic is like this one, or exponential is like this one. Both of them are possible. So quadratic or exponential. And the second one, so we know for exponential function only two scales. This is the first one, this is the second one. So this one does not look like this one. So this is just a quadratic. And for the third one, logarithmic or quadratic. And the last one must be a quadratic. Alright, so next part, let's go to section 1.10, logistic function and models. Let me see. For a logistic function, a logistic function has the equation of the form L divided by 1 plus a multiplied by e to the minus b x, b multiplied by x, where a and b are non-zero. So a and b, they cannot be 0. And a and b are constant numbers. And L must be positive. It's the limiting value of the function. So for a logistic function, the limiting value of the function is just the denominator, which is L. And this function either increases towards an upper limit or declines towards a lower limit as the input value increase. And the graph for a logistic function, it has two concavities. So now, never mind. This is two concavities, because we know if a function has two concavities, then there must be an inflection point, because inflection point is the point where the concavity changes. We have a 2, then that means we must have a point. That is the special point where the concavity change. So an inflection point is the point where the function is increasing or decreasing the most or the least rapidly on an interval around the inflection point. So, and the function decreasing or increasing, it depends on the sign of b. B is this one. So pay attention to the index to the power is negative b. So if it is e to the 2x, then that means b is negative 2. If it is e to the negative 2x, then that means b is positive 2. So, and then this part is the horizontal axis. Oh my gosh. The function is bounded by the horizontal axis and the limiting value. So for a logistic function, it has two horizontal asymptotes. One is y equals to 0, no matter what is the value of L is. That means as long as the function is a logistic function, one of the horizontal asymptotes must be y equals to 0. And the other asymptote is just y equals to the denominator, which is y equals to L. And alright, so let's see the function graph. You can see this is the first type of a logistic function, and this is the second type of a logistic function. But no matter which one it is, it always has two horizontal asymptotes, y equals to 0, and the other one is y equals to L. So similar, y equals to L, the other one is y equals to 0. The only difference is that for this, the first one, when x goes to negative infinity, then the function stays as L. But for the other one, when x goes to positive infinity, the function stays at y. And let's see, logistic function. And for this one is logistic function is just a b, and then the rest part is the same. So for example 4. Alright, example 4. So this is the full question. And also for this kind of question, the first step is to try to draw the scatter plot. So for this one, after you draw the scatter plot, then you can see actually for this one we have two concavities. So we have to use a logistic model. And the model is just the v of x is equals to 10,000 divided by 1 plus 99.015 e to the minus 3.676x. And the unit is just 1,000 computers. The computers at an international company. Were infected by a computer virus. X hours after the virus is detected. And with x is from 0 to 2.5. And the next one, write the equation of the two horizontal asymptotes. So one is always y equals to 0 as long as this is a logistic model, and the other one is just y equals to the denominator, which is 10,000. And the next one, 3 hours and 15 minutes later, it will be 9.994, and the unit is 1,000 computers. The next one, you have to use the math solver. So that means y1 is 5.5. So because pay attention to the unit, it's 5,500, and the unit of x is actually 1,000 computers. So this one, you have to use the 5.5 instead of 5,500. So for this one, we have x is 1.315. And next one, cubic functions and models. And this is the last example. This is the last model in this section in chapter 1. A cubic function has a cubic one. No, just that's weird. So I thought cubic is right after quadratic, but there's a logistic model in the middle between quadratic and cubic. A cubic function has the equation ax squared plus bx plus cx plus d, where the first term, the coefficient of the first term cannot be 0. That is, a cannot be 0, and b, c, d are just constants. So this one has an inflection point, because it's the function shows a change in concavity. If a is negative, the function is concave up, followed by concave down. So that means if the a is negative, then the function first concave up, then concave down. If a is positive, then the function first concave down, then concave up. And the end behavior, this is the end behavior. All right, so let's see one example. So for this one, we have, you can see we have different types of even though this one concave down, concave up, concave down, concave up, but both of them has an inflection point. This is inflection point, inflection point, inflection point, and inflection point. But this one is increasing all the time, but this one increasing, decreasing, increasing, decreasing, increasing, decreasing, decreasing all the time. So these are two different type of functions, but they are the sum of a are the same. You can see this point is the point where the function is increasing least rapidly. Then similar, this is the function, this is the point where the function is decreasing the least rapidly. And this is the function where, this is the special point where the function is decreasing the most rapidly. So this is the point where the function is increasing the most rapidly. Then example 4. So this is the strategies for, let me see. Here's the, all right. For the cubic function, for the cubic function, it's the 6. This is the model. And then page 73. Strategies for choosing best fit function to model a data set. First, we need to look at the coverage of the scatter plot. So the first step is to draw the scatter plot, and then we look at the curvature. If the function has no curvature, then that means the function is a linear function. If the function has only one concavity, if the function has only one concavity, that means the function has no inflection point. Then it is the quadratic, exponential, or logarithmic function. All three of them are possible. And if the function has two concavities, two concavities means there must be an inflection point. Then that means a cubic function or a logarithmic function. Both of them are possible, because now we have for example, the second one, we have 3 options. Then we have to make sure we have to only pick up one. Then let's check the second step. Find the best fit among the functions with the same amount of concavity, and then consider the last step. We just consider the end behavior. That means when x goes to infinity, what is the function behavior, and the given context in choosing the best functions to model the data, especially if two functions fit the data equally well. Then if the two functions fit the data equally well, we just check the end behavior. Example 4. So example 4, the first one, you can see the pattern here. It looks like a quadratic function or a logarithmic function, because a quadratic function is like this one. So this is just a part of it, and the logarithmic function is like this one. So this is also the other part of it. So we don't know which it is, but just it's possible. And the second one, because we have an inflection point, two concavities, so cubic or logistic. And the next one is, of course, a linear function. It's just a line. Then example 6. First, we draw the scatter plot. logistic and cubic function. Then this one, B and C, the answers may vary. So I just give you a example. This one, if it is a logistic function, if you use logistic model, then the answer should be about this one. This one gives the unit is percent. Gives the this is the cubic function, and the last page of the cubic function is actually the summary of the 6 functions. So I think most of you have them filled in. So this is a table for you to prepare for the exam. Make sure you know how to draw the graphs and the special features. Special features is like, for example, this one has no concavity. And how many concavities? It has only one concavity. And what about the let me see. So actually, you can just check the textbooks to fill them in. And this one, for example, this one, it has 2 concavities. It has 1 inflection point, and the horizontal line. So what about the horizontal line of this one? How many horizontal lines? How many vertical lines? What are they? This one is y equals to 0. The other one is y equals to L. So then let's go back to section 1.6. 1.6 Models in Finance. That's page 36. So for this one, we talk about 3 models for the interest. The future value, the notation is capital F of t, where t represents the amount of time since the investment was made, and pay attention to the unit of t must be in years. And the p represents the present value, and it is called the principal of an investment, or you can say this is the face value of a loan. And then we know f of t is the future value, where t, the unit of t, must be year. In year, that means if you are given, like, for example, 6 months, then you know it is just a 0.5 year. You have to change the unit to year. And then R is the APR. It's called the nominal rate of interest. And this is the first one, this is the second one, and this is the last one. The first one is a simple interest. So the simple interest is just the principal plus the interest. And the second one is the compound interest investment. And the keyword is n times per year. So compounding of interest occurs when interest is earned on previous interest. So the function equation, the formula is just this one. P multiplied by 1 plus R divided by N to the nth power. Dollars, the unit is dollars. And N here, N just means n times per year. And the T is in years, T years. And R is just the nominal rate of interest. It must be in decimal form. So this is the second. N is the number of N is just means n times per year. And the last one is about the continuous compound interest investment model. So this one, the model is just a P multiplied by e to the RT's power. Unit is dollars, where R is the nominal rate of interest. So for continuous model, this is easier. So basically, if you in the question, if you see the word like semi-annually or like quarterly, then that just means, okay, we are using the second model because you are given the information of the value of n. So n times per year is given directly. If you see the model size, all right, this is something continuously, then that means we are going to use the third model. Normally the third one is a little bit, it's not that complicated. Example B, the second model is a little bit more complicated than the continuous model. So for example 1C, 1A3. So you can see this is from the keyword here, compound quarterly, so that means n is 4. When n is 4, so let's read the question. To find the value of the investment after 19 months. After 19 months, so for this one, because we are given the value of n is 4, then we know 12 divided by 4 is 3 months. So that means you can only choose your answer every 3 months. You can only get your money back every 3 months. So that means 3, 6, 9, 12, and then 15, 18, 21, 24. So that means this is about an investment. For the investment, let me see. 19 is right here, 19 months. So now you have to make your decision. Which one do you use, 18 or 21? Because n equals to 4, so that means you can only choose the month that is a multiple of 3. So now 18 and 21. But because this is an investment, so investment, you have to choose the previous one, that is 18. If this is a loan, pay attention to the difference. If this is a loan, so that means you have to choose 21. If it is an investment, then you have to choose 18. Okay. And then let's see example 2. Example 2, we are given the principal is the $100. Excuse me, $1,000. This is an investment. The APR is just a 4.2%. The first one, right? Okay, this is the question. Find the time. What is the value of t when the investment is doubled? If the keyword, if the interest is compounded quarterly, so that means n is 4. So write the equation. The principal is $1,000 multiplied by 1 plus r. Pay attention to the APR. It must be 0.042. It cannot be 4.2%. Then divided by n times per year by using n. The value of n is 4. Then the power is nt. N is 4. T is just t. Because we are looking for the value of t. When the investment is doubled, original investment is $1,000. So when it is doubled, it must be $2,000. So $2,000, then you can see, all right, for this equation, we have only one unknown value, that is t. So just use math solver. And then after you use math solver, then the solution is 16. So the math solver, so you can see this is the instruction. This is our y1. Just type the equation here. Then we use math solver, math 0 or math b. So math solver, because we are looking for the value, y1 is 2,000. So y1 equals to 2,000, or y1 minus 2,000 is 0. Then we solve it. Then you can see this is our solution, 16 point blah, 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 blah. So we know, let's rewrite the solution here, 16.5899, just use the 3 decimal places. Then that is 590, or years. But we are not done, because the question is asking the number of years and the number of months. So the integer is just a 16. Then we know for sure it must be 16 years later. Then what about the decimal place? Here, we have two methods. The first one, about the 3 decimal place, we just use 590 or 5 multiplied by 12. Then we got about 7 point something. So this part is about the months, but pay attention to the value of n is 4. So that means you can only choose 0. 12 divided by 4 is 3, so you can only choose 0, 3, 6, 9, 12. And the 7 is between these 2, 0.0 or something. And then, so the question is, which one do we choose, 6 or 9? So, because, alright, this question asks you, how long does it take your investment to be doubled? If you choose 6, 7 is the exact number. If you choose 6, then that means when you plug in x equals to 6, your investment is still less than $2,000, because 7 is the first time your investment is doubled. So that means you have to choose the next one, 9. So the answer is 16 years and 9 months later. And then you can see, for the second method, you can just use the table to find the doubling time of the investment. So again, this is our y, and then we use the second window, that is the table side. So you can see, side both of them are auto, then you can see, all right, the first one, 16.5, the answer is 1992.5. And the second one, the next option is just a 2013.4. So for this one, this is the first time your investment is doubled, so we have to choose 16.75. That means 16 years. 0.75 is the multiplied by 12. Then we got the same answer. That is 9 months later. And the next one, B. Find the time it takes the investment to double. Now, we are not using the second model. We are using the third model, continuous model. So initial value, P is just $1,000. Then e to the R is just the 0.042t. And the investment is double, means 2,000. So we just solve for the value of t. Then the answer is just 16.504 years. Because for this one, this is a continuous model, so we don't have to consider which option we use. Just use this answer. You don't have to consider which means we choose, the previous one or the next one, because this is a continuous model. We don't have to consider it. Then about the APY. So for APY, for the two formulas of APY will be given for the test, so you don't have to memorize it. And just pay attention to the keyword. If it is a continuous model, then if the question asks you what is the APY for this continuous function, so just plug in the value of r, then you are done. Because this one is only a function of r. E means a constant number. And if this is a compounded model, like quarterly or semi-annually or yearly, then we know the corresponding value of n. Then you just plug in the n here and the r here. Then this is the APY for the second model. We don't have the APY for the first simple interest model. Then let's see example 4. So example 4, the keyword here is quarterly, just means n equals to 4. So this one asks you that how long, let me see. Okay, so this one says this is our r, which is 0.028. This is r, and this is n is 4. The future value. Oh yes, okay. This is a different question. So that means all right, we know that 5 years later, our investment will be $5,000, and the question is asking you what is the investment now. What is your initial investment? What is your original investment? So it's like, all right, suppose our original investment is just $P. Then we plug in the R, that is 0.028, divided by n times per year, that is 4. Then NT is just 4 multiplied by T. T is given just 5 years later. But because the question is not asking for the value of T, or is not asking for the value of like 5 years later, what is your investment? This one is asking you what is your original investment. 5 years later, your investment will be $5,000. So the question is asking what is the value of P. You just use math solver. So we solve for the value of P, that is 4,348.292. The next one. This table is a very good exercise. So since the solution is given, then I just recommend you to finish this table one more time. So for this one, I'm going to talk about the semi-annually. Let's see this one. This one, the formula is just a P, because we are given the value of P is just 5,000, so it's $50,000 multiplied by 1 plus R. 5% is just a 0.005. 0.05. Divided by n times per year, semi-annually just means n is 2. To the nth's power, 2, n is 2, t, it's just t. So, but this question is asking, after 23 months, semi-annually just means n equals to 2. Then that means 12 divided by 2 is 6. You can only get your money every 6 months, 0, 6, 12, 18, 24, and 30. So 23 is between 18 and 24. So for this one, because this is your investment, you have to choose the previous one. So 18 divided by t, the value of t is just 18 divided by 12. You cannot just plug in 23, you have to use 18 divided by 12. And the future value is just 53,844.56. Excuse me, 53. And this one, how long does it double? So the value of t is just 14 point. After you use math solver, you get the value of t is just 14.036. And then, so it just means 14 years later. Then about the decimal places, multiply by 12, and then choose the optional 36. Choose the possible solution, 36 mass. So similar, just try to redo the other examples. Alright, and that's all for the review of chapter 1. And the next video we're gonna finish chapter 2, then chapter 3, then chapter 4. And the exam is next Wednesday night from 7 p.m. to 9 p.m. Alright, thanks for watching.